Okay, good morning. Let's start the lecture. Okay, we'll finish the application of a double integral today, and then we'll get on to the triple integral concept today. Okay. We covered quite a few examples of applications of a double integral from previous lecture. If you recall, basically, I won't write all the formula, but we have covered how to basically look at how to calculate area, okay, using double integral. And we also looked at how to calculate the mass of a thin plate. The concept of average value of a certain function over this region R, and this can be easily extended to different concepts. Average temperature over a region R, average height over the region R, right? Or average distance over a certain region R. So this is a very useful concept. And then we have this weighted average of the function f over the region R. Okay, so similar concept. And then from here, we looked at the center of mass, x bar, y bar. So the formulas, you'll have all of the formulas in the final exam. But while you're doing assignments, I encourage you to basically try it a few times, and at least at this stage, you can memorize all of the formulas. Okay. Yeah. And at the end, we look at the last application, which is the moment of inertia. In this particular case, because it's a thin plate or area we're looking at, so we're talking about the moment inertia of not a 3D object, it's moment inertia of an area, okay, or cross section. So this is the moment inertia of the area, and more precisely, this is also called second moment of area. Okay. Now, we'll look at a couple examples for this last application here today, okay? So basically we have three different situations in here. One is essentially the moment of inertia, okay, MOI. Okay. First is the moment inertia about an axis, okay, through origin. Okay, but an axis through origin. Well, in this particular case, basically it's the z-axis. Okay, because if the region is in the x-y coordinates. Okay, if we have a region R at here. So we're talking about axis. An axis going through this origin, basically it's the z-axis at here. Okay. And then what will be the moment inertia about this area? Okay, rotating about this z-axis. And the formula is I equal to, sometimes we use J, but so J or I, okay, equal to integral, it's double integral x squared y squared, delta is the density times dA. So if you pick any point here, and that's your radius, and this is basically is your x squared, r equal to square root x squared plus y squared. That's the distance from that point to the origin, right? And over here, this essentially is the r squared. Okay, so that's the formula for calculating this polar moment of area. This is basically polar moment of area about an axis going through this origin at here. Okay, yeah. So that's the first moment inertia formula, and the other moment inertia is moment inertia, okay, about of the area, okay, about x-axis or y-axis. So the rotation is about the x-axis now, or y-axis, instead of about the z-axis. And the formula slightly different. You have Ix, so this is your x-axis, this is Ix, this is Iy, okay, notation-wise. Ix representing moment inertia of area about the x-axis. Iy is the moment inertia about the y-axis. Ix is double integral over the region R, integrating y squared delta dA. Delta is the density function. And what is y squared? Because if you pick a point, okay, and you look at the distance from that point to the x-axis, it's y distance. Okay. And second moment of area, second moment of area basically is about the area times the distance squared. I mean, that's why they call the second moment. And the first moment you have just area times the distance. Similarly, you have Iy x squared delta dA. So there are a whole bunch of formulas in here. Okay? So given the question, really carefully at what you're required to calculate, and you apply the formula appropriately. And once you have the formula right, and essentially the rest of the work are basically just a double integral. Right? There's no difference from any other double integral. Right? You either choose Cartesian coordinates or choose polar coordinates, right? And you carry out the rest of the computation, okay, and easily. So let's take a look at a couple examples here in terms of the moment inertia example here. So let's say we have a thin circular disk, and here is the circular disk. It has a radius of A, and we place the circular disk, okay, at these xy coordinates centered above the z-axis. Its density delta equal to 1, so there's a unity density across the whole thin plate. And I wanted to calculate basically what is the moment inertia of this thin plate with respect to the origin, O at here. Okay. So what's the moment of inertia, okay, about origin O? So when you see about origin O, basically it's about the z-axis. So moment inertia is always about an axis. With respect to different axes, then you get a different, basically, moment inertia. let's apply our formula, okay, to calculate this question. This is actually a very simple question, but it leads to the next one actually. Okay. Since it's about the origin O at here, okay, according to the formula, this is the one we're looking at. Okay, so this one here, and let's put that down here. So integral about r, and then x squared plus y squared times delta is equal to 1, so I'll just use the dA at here now. Okay. Your R essentially is this circular disk. That's your double integral calculating this moment inertia about origin. Now, then the next step is regular double integral procedures. You know, whether you choose Cartesian or polar. In this case, because the region is a circular region, so most probably 99% you'll choose polar coordinates, right? So choosing polar coordinates meaning you will replace x with r times cosine theta, replace y with r times sine theta. At the same time, your dA will be replaced with r dr d theta. Okay. So that's how you transform everything from Cartesian into polar. Once you get this step, the next step is to find the limits for r and theta. As we learned in the procedure, so what you do is starting from origin, you draw a reading line out of this region R. First contact give you the R mean, second contact give you the R max. Apparently R mean is 0, R max is A radius. Then you rotate this reading line, okay, starting from x-axis across the whole region and find the two edges covering this whole region R. In this particular case, when you start the x-axis, it's already as the initial basically edge, and once you finish, so that's the other edge. So it's 0 to 2 pi. A very simple trigonometry identity in the middle here, taking out the common factor r squared, you got a sine squared plus cosine squared, which is 1. Basically you're integrating 0 to 2 pi, 0 to a, r squared times r dr d theta. Okay. There's no trick at all, so you can get an answer which is pi a to the power of 4 divided by 2. So that's the moment inertia of the thin plate, which is already centered around the z-axis, and this moment inertia about the z-axis here. Any questions so far? It's all good? Okay. Okay, so now let's change this question slightly now, okay? Yeah. The next example. We're going to use the same thin plate. And I'm going to put this thin plate, okay, in a 3D perspective. But this time, instead of calculating the moment inertia about the z-axis, and I'm required to calculate the moment inertia, okay, of the thin plate about any vertical axis through its boundary or through its edge. So it's not about the, basically it's not about, it's about a different axis now. Previously it's about what? Previously it's about an axis through the center, right? So an axis through the center of the thin plate. And now we're talking about an axis passing through any point, okay, any point on the edge of this thin plate. So what would that moment inertia, okay, for this situation, okay? Yeah. So let's call this axis U at here, okay? What will be this moment inertia about the axis U? Okay, So there are infinite number of axes, you threw the edges there. To calculate the moment inertia, you always have to put it into certain reference frame in order to be able to calculate that. So mathematically what we can do is, let's put that into a frame at here. And basically what I'm going to do is, I'm going to replace this u-axis, okay, with the z-axis. And then we create anything you want here. You can create an x-axis and a y-axis. Not here. Sorry. Looking from the top. Okay, let's do this. Looking from the top. Okay. Here is the thin plate. Attach an xy coordinate system to this thin plate, and then the u-axis, right, is the one going through the origin and here, which is basically the z-axis in this case. Okay. So it doesn't matter which point the axis goes through. You can always create an xy coordinate system attached to the point like this. So essentially more or less like that. So if this is your y and this is your x, but it's not, axis should be this way here. Okay. Does that make sense? Well, they're looking from the top. But anyway, so you'll be able to create a xy coordinate system attached to thin plates like that. Okay. Yeah. So now we're talking about basically this thin plate. This is A here, then this is 2A, about an axis going through this origin over here. So we turn this original question into this perspective. Okay. So let's apply the formulas, okay, in terms of calculation. So again, it's about basically, if you pick any point, you have a distance from that point to the origin, which is r at here. Okay. So again, you're turning this question into a similar question like previous. So what's the moment inertia of the thin plate with respect to the origin now, right? And with respect to the axis passing through the origin. I use the same formula now. So I equal to r squared and then dA at here. Still consider delta equal to 1. Okay, density equal to 1. Okay. 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 So now let's look for limits. It's a still circular disk. I think I'm still gonna stick with polar coordinates. So let's look at the limits now for this double integral. Here's the region R. Okay. To find the limits, as we have done previously, we start from origin, then we draw a reading line out of this origin here. First contact give us the R mean, which is 0. Second contact give us the R max. Is there still going to be 2? No, right? If I draw it here, draw it over here, they're different. So we had to find an expression for R max, basically. This is a very similar assignment question to this one here. Okay? So what would be the expression for R max? Always rely on the geometry that you can find within this question. Okay. You're talking about polar coordinates, so you're talking about r and theta. So theta is always the angle from x-axis counterclockwise to where the reading line is. So that would be theta here, right? And then this portion is where you're looking for. This is the R max. Okay. So use what's known, what's unknown, and sometimes you have to create a certain geometry to help you with finding the solution here. And so in this case, we can create a triangle here, okay, by connecting that point to the other side of this circular disk. As you learn in high school, what's the nature of this triangle here? Sorry? It's a right triangle, right? Yeah. So when you create a triangle with this diameter as one side, okay, and it's naturally a right triangle, a right angle, basically. Is that good? Yeah, that's actually very useful. Okay, I tested a similar question last year in the final exam. There's a similar question in the assignments, but unfortunately, there's still a lot of people who couldn't figure out or not aware of this simple geometry here. So once you have this one, then you can make use of the triangle here, because this side is how long is it? 2a, right? Yeah. And here is theta here. So R max is equal to cosine theta equal to R max over 2a. So R max equal to 2a times cosine theta. So that's your R max, and that's why R max is a varying quantity, right? It's not a constant here. So let's put R max over here. That's your 2a times cosine theta. Second step is to find the theta limits. Now you rotate this reading line, okay, starting from x-axis, okay, start to rotate. Find where are the two edges sandwiching this region R. So in this case here, where are the two edges, or where are the two special reading lines sandwiching as the boundaries for this reading region R? So not here, right? If you go up to this and here, so that's the two boundaries, or the two edges sandwiching this region R. Okay. So the question here is, what will be the angle associated with the two edges? And I find it interesting, in the past there are different ideas in terms of angles at here. What do you think? What's the angle associated with R mean and R max? Exactly. Yes, that's great. So theta mean is negative pi over 2. Theta max is pi over 2. So this is a consistency is a very important thing right here. Okay, consistency. So what we choose here is negative pi over 2 to pi over 2. And where's negative pi over 2? Is from here to here is negative pi over 2. And then from here to here is pi over 2. Does that make sense? Right? Okay. Can you give me another option for theta mean and theta max? Louder, I can hear. 90 to 270? Yeah, 270, that's right. 3 pi over 2, right? Excellent. So the other option is, right, you follow exactly the convention for theta angle. So you go from here to here, that's your first edge, right? It's pi over 2. So the other option is pi over 2. And then from here you keep going. Basically from here you keep going here, here, here until here. Right? So this you're always going counterclockwise this time. It's first pi over 2, and then second when it comes over here, how much now? 3 pi over 2. Right. Yes?
The region we are talking about is on the
Yeah.
So if we go from pi over 2 and 3 pi over to that cover the area of the left side. This is it.
If you mean reverse the limits here?
No, I mean this part of the integral is you integrate from, it's pretty much the negative x-axis. That's the region.
So what's your theta mean theta max? Sorry, I didn't get it.
Like, I wonder if that's okay, because like your region is on the positive x-axis.
Yeah.
Your limit, you put it on the negative x-axis.
Yeah.
Is that okay?
Would those values pop out a negative value for your integral?
Oh, right. You are absolutely right. That's a mistake. Good point. Yeah. So if I do pi over 2 to 3 pi over 2, I'm integrating the other side there, right? Yes. So what should it be actually? 3 pi over 2 to where? Huh? To pi over 2? Well, you cannot have a theta max less than theta mean, right? Ah, excellent. Is that good? Yeah. I think this is a little bit more tricky than this. Yeah.
Couldn't you do pi over 2 because pi over, like cosine pi over 2 is the same as cosine 5 pi over 2?
Consistency.
Oh.
Right. So if this is your starting point, that's your end point here. So you got to be consistent, right? So you go, this is your starting point, and then keep going until here, your end point. Yeah. Yes. Yeah, you will have the same answer. Yeah. So what's the easy one? I think this is probably the easier one, right? Yeah. So this, you won't make a mistake from here. Consistency. So either use all positive angle, or you use from a negative to a positive, like this, like here. Good? Okay. Excellent thinking. And so from here, the rest of the work actually seems to be okay, but you will see there's a little bit a hiccup in the next calculation in here. So this is R cubed, and then you have limits from 0 to 2a cosine theta. R cubed, you get R, so 1 over 4, R to the power of 4. Substitute 2a cosine theta into it. So we got this quantity here, right? And then substitute into the limits. A cosine theta is coming into here. 2 to the power 4 is 16. So 16 divided by 4, you got a 4 here. So 4a to the power 4, and then cosine theta to the power 4, and then d theta. Okay, so that's what I mean. Once you calculate the inner integral, you'll get a results like this. Okay. Now this integral, if you have it in the midterm or final, you probably shouldn't spend too much time if you don't have a formula or if you don't have a clue of how to do these kind of things. There are two different ways. I actually won't give you the details how to get. You can take a little lecture notes. There are two different approaches. One approach is to use integral by parts. So one approach is, because this is a cosine theta to the power 4, you can do an integral by parts to calculate. Okay, so take a look at my lecture notes here. Okay. And the other approach is formula. Okay. So you have formulas basically in general. What is the cosine theta to the power of nth integral? So there's a general formula for cosine theta to the power of n. And the formula is written as this. Great. Right, so that's the formula. If there's a such question, you might be given the formula, okay, for this kind of question. So you don't have to sweat too much for now. Okay, so don't worry about this. Basically, plug a 4 over here, and you may have to apply this formula a couple of times because it's kind of embedded here, right? But you will be able to get the answer. So the answer from here is you get 3 over 2 pi a to the power of a 4. It's a very simple question, but the computation may be a little bit cumbersome. Any questions so far in terms of the moment inertia calculation? Okay. You just have to know what moment inertia you're required to calculate, with respect to the O, or with respect to x-axis, or with respect to the y-axis. As a matter of fact, in your first year dynamics, okay, or statics, I don't remember which course, when you calculate moment inertia, there is another one is so-called what? Parallel axis theorem. Do you learn this one here in your first year? Yes? No? Really? No? Parallel axis theorem basically says this: moment inertia about certain axis u equal to the moment inertia about its center of mass, then plus, in this case we're talking about area moment inertia, so plus the a times d squared. That's parallel axis theorem. So this one here is the moment of inertia. In this case we're talking about area here, okay? Or second moment inertia with respect to axis u. Okay, so respect to axis u. And here is the moment inertia with respect to center of mass. And then here, this is your area, because we're talking about area here. Okay, so parallel axis theorem also apply to 3D objects. Then in that case, you times the mass, basically. And then here, d, this is the distance. Okay, this is the distance from center of mass to axis u. Okay, so that's parallel axis theorem. This one often in time comes in very handy if you have the quantity for moment inertia about its center of mass. And then all you need to do is just look at what's the distance between the axis u and the center of mass axis and its associated area. So for example, in this particular question, we have actually calculated center of mass, right? The moment inertia about center of mass, which is from here. So that's moment inertia about its center of mass here, because in this case delta equal to 1, so origin happened to be this center of mass for this same third circular plate. So that's your ICM, pi over 4 over 2. So if I use this one here, so IU equal to pi over what? Short memory. Pi a4 to 2 over 2. Okay, so that's your I in terms of the with respect to the center of mass, and the area is pi a squared. That's your circular disk, and d squared is the distance between center of mass and the axis u. So in this case here, what's the d? So it's between center of mass and the u at here. So that's a, right? Times a squared. So you put all these together, you get exactly the same answer, okay, as the regular calculation. So this is a very useful tool. And more often, the moment inertia about its center mass can be easily looked up from any mechanical engineering handbooks, okay, for regular type of geometry shapes. So you can use this to calculate arbitrary moment inertia with respect to the general axis U. Is that good? Yeah, so this can be applied to 3D object later, we'll see. Another thing else I wanted to point it out here is there's another interesting observation, and you probably noticed that. But before we see that, there is a principle, okay, physics principle, which is the so-called conservation of angular momentum. Okay, so conservation angular momentum. This is basically a theory, but it's only the angular momentum is only conserved if there is no external torque. Okay. What's angular momentum? Basically, when you use your moment inertia multiplied by the angular speed omega, and that's your angular momentum, basically. It's very much like what? Linear momentum. What's linear momentum? Linear momentum equal to the mass times velocity, right? Yeah. So, what's this so useful? Anyone of you does figure skating right here? No? No. Anyone of you watch figure skating? Okay, you do, right? Yeah. So what do you notice? Most of the figure skating, the girls are typically what? Small size, right? Yeah. And more so when they do the spinning, when you watch TV. So when they do the spinning, there's a move is they spread out their arm, and then they shrink their arm to the middle of their chest. So what happens when they do that? They rotate faster, right? So if they want to rotate faster, what do? They have to do this. When they do this, what happens then? Because angular momentum is reserved, its momentum is conserved, considering very little friction on the icing rink. The I is smaller now when your arms are all kind of cramped in the middle of your chest, right? And then your omega will tend to get to a greater value, basically. Okay, yeah. And if you go to a science center, actually I took my kids to science center a couple of times in Vancouver. There's an experiment, right? So there are two discs. One disc, basically, both discs, you have a few masses you can move around from the center to the edges for the disc. So basically you can experiment which will rotate faster when you put all the discs in the center of the disc, or when you spread out the smaller disc, right, spread them out to radiusly to all the edges of the disc. So basically it's like a disc here, and then you have a smaller masses attached to the disc, okay, and you can move around the smaller masses either to the center here or to the edges of there, right? Yeah. And the kids can literally see when you spread all out here, what happens? Do you think it's going to be a slower or faster? Slower, right? Yeah. You have a higher, basically, moment inertia now. Right? So that's the idea of a conservation of angular momentum here. Okay. Yeah. Any questions so far in terms of the application of double integrals? Okay. Good. Yeah. Good. So I spent a little more time on the application of double integral because when I finish this next triple integral, I will actually skip some of the detail because it's very easy extension from basically all the concepts we cover here will be easy extension from double integral to triple integral. Okay. So now having said this, so let's look at the triple integral now. So first, let's look at where triple integrals from and what exactly we can use triple integrals for. Let's consider ourselves a 3D region. So here is, instead of a flat region R, we're consider now a 3D region D now. Now this region D, okay, in our case, needs to be bounded. It's not a infinite region D. And then we have another thing to consider. Also consider there's a function. Okay. This function is f of x, y, z, and this function is defined over region D. Okay. So this is purely mathematical description. You got a region D, and you got a certain function essentially associated with this region D. So what does, if you recall that, what does a function, what does it mean by a function is defined over a region D, right? What does it mean? It means whenever you pick a point inside, any point inside the region D, okay, let's say call it xi, yi, and zi. Okay, let's call it a point inside region D. And when you plug this point into this function f at here, you get a value, right? That's basically what it means by defined. You not get a, if you get an infinite, then that's not a defined. Okay. So in our case, it's always defined here. Okay, so then f of xi, yi, zi. Okay, that's basically will return. It returns a value. That's what it means by define. So now let me temporarily get away from the pure mathematics. Let's give it some kind of physical meaning at it here. Okay? So let's assume this function f of x, y, z. Assume it is the density here. Okay, let's assume it's a density function. So what it means is basically you pick any point inside the region D, then you know what the density at that location essentially. Okay. So you see the difference now with the double integral with the previous cases. When I have a region R, I can plot it in 3D. When I have a function f of x, y, I can plot at the same time as the region D, right? But this time, I have a region D, which is already in 3D, so we can plot it, no problem at all. But this function f of x, y, z, that we can't plot it anymore, right? We can't plot it together with the region D. It's somewhere. If you have a fourth dimension, you can plot it, but then you can't visualize. Our mind doesn't work like that. So we basically can visualize this is something aside from this dimension here, but it's associated with the value, with the points inside the region D. Okay. And density is a concept like this. If you put at any point, you get a density here. So now the question here is, what will be the mass of this solid, okay, described by a region D? And that's a simple question. What would be the solid of this object described by this region D at here? So here's what I'm going to approach this question here. I'm going to use the limit concept, try to estimate first, and then use the limit concept to get a precise information. If this is a point x, I, y, I, z, I is a point inside region D, then I'm going to construct a small cube, okay, around that point x, I, y, I, z, I. So here's a very small cube at here, and this small cube has essentially three sides: delta x, delta y, delta z. So you give it a small segment around this point x, y, y, I, z, I, create a small cube. Essentially what we get here is we get a small volume, delta Vi. And this small volume equal to delta xi, not delta x, delta x, delta y, and delta z. That's your delta V. The small mass associated with that cube is the density at that location times the small volume delta Vi. So you get density times, consider it's a small cube, then you consider even density within that cube. So you get small mass. So then the total mass will be approximately an addition of the number of cubes, whatever number of the cubes inside the region D. When you add them up, you get the estimated total mass. Okay, so that's the idea of estimation. We did a similar estimation previously when we start covering double integral. Now I'm going to let the n go to infinite. Okay, so then instead of estimation now, you have a precise description of the total mass now. Summation sign will become integral sign. But we're dealing with this delta V here is delta x times delta y delta z. So when n go to infinite, the delta goes to straight D, differential. Sigma goes to basically a triple integral at here. Okay. So now my total mass is equal to a triple integral, integrating with respect to the given region D, and integrate this density function and dV at here. dV is the small volume, differential volume here, so it can be dx, dy, dz. Now this is basically triple integral at here. So you can see we basically have extended from 2 variable to a 3 variable. We added essentially one more integration at here. Okay, that's the only difference. Okay. Okay, now of course another difference is instead of a flat region R, we're dealing with a solid region D at here. First, actually, I will give you, let's look at the very special case. So what if this function is equal to 1? So equal to 1 basically means if in terms of density, you have a unit density across the whole region D, right? That's what equal to 1 means. If this equal to 1, then this integral becomes just this, right? Triple integral over the region D and then dV. So what do you think this integral will give you? Volume. Okay, excellent. So integral, if you learned in single variable, integration d anything equal to that anything inside the bracket. Doesn't matter whether you have a triple integral or double integral. Okay, the same idea okay, applies. As a matter of fact, if you look at some of the reference book, they don't differentiate the symbol-wise. They don't differentiate the single integral and multiple integral. So some textbook always just use one integrand symbol here, applied to any situations. So integrand R, integrand D, right? Anything. So that's another. Some other textbook do this. Okay. Yeah. Okay. So let's look at basically the computation-wise now. Okay. Yeah. We're going to look at actually a few examples here. Three different systems. We're going to look at three different systems. Three different systems. So we're going to look at three different systems to evaluate this triple integral here. The first one we're going to look at evaluating triple integral in Cartesian coordinates. So that's the first one we're going to look at. How do we evaluate the triple integral in Cartesian coordinates? I want you to bear in mind the idea of integration, right? This is integration over region D. The idea of integration is to scan through this region D. Just like a double integral, you scan through the region R. And just like single function from A to B, you scan through the range A to B. Okay, so it's all about how you can scan through this region D at here. So I'll list a number of steps, okay, to illustrate essentially the idea of scanning through the region D. Now, step number one, okay, you got to decide on the order of integration. Just like double integral, dx dy or dy dx. So what are we going to pick? In this case, your dv can be dx, dy, dz. It could also be what? dy, dx, dz. So you have three things that are here. How many combinations do we have? You're in probability now, right? Total sample 6. Okay. So you have so many choices, just pick one. Yeah. But typically maybe this one will work. So sometimes as I said, Cartesian coordinates, a lot of the time, it doesn't matter which order you pick. Okay? But a very extreme case, the order maybe matters. Okay. Step number 2. Once you decided on the order, then we need to basically to identify the limits, okay, for the variable. Actually, more so in my lecture notes or assignment solutions, I pick dz, dy, dx as the order. Okay? Yeah. So I'm going to use dz, dy, dx as the order here to illustrate how you find the integral limits. So that's your step number 2 to find the limits. But before you can find the limits, the first actual step number 2 is you got to sketch this region D out. You have to sketch it out. If you don't sketch it, most of the time it's hard to visualize in our head. And you're not only just going to sketch the region D, you're also going to sketch its shadow, okay, in the xy plane. So why sketch the shadow only in the xy plane? It's because of, as you're going to see it next, it's because the order here. because we try to find, in this case, we're trying to find the limits for the z, and then we'll try to find the limits for x and y, for y and x, right? So if this is the order here, and this is y, you're going to sketch its shadow in the xy plane, because the y and x limits will be found depending on its shadow in the xy plane. So that's basically the last two variable, okay, depends on the order you picked, is where you're gonna sketch the shadow. So what does shadow mean? Shadow basically means you project the whole region D, okay, into xy plane as a flat region, okay, like in a AutoCAD, or in a CAD drawing, you have a view of the projection in certain plane, basically. Okay? So that's what shadow basically means. And most importantly, also label all the boundaries, okay, for the D, okay, and shadow. Let's call it shadow is R here, okay, and the shadow R. So label all the boundaries, and the question typically will give you the information in the boundaries here. For example, right, I'll give you an example here. This is just a generic example. So let's say I have a solid region D, which let's look like this, for example. So that's your region D. Okay. So what this region D does is more like a cylindrical things, but then the top has a surface z equal to, let's call it f2 xy, and bottom here is z equal to f1 xy. So there are two surfaces, one at the bottom, one at the top, right? So these two surfaces are described by f1 xy, f2 xy. And when you project this whole region D into the xy plane, so theoretically maybe you're going to get a certain shadow like that. And for this shadow, what you may get is you have maybe there are two boundaries associated with this shadow R. So let's call this is y equal to g2x, and then the other side is y equal to g1 of x. So when you project everything into the xy plane as a shadow, and that's what you get. Okay, this is your shadow R at here. So that's what I mean by this is not it is generic. So sketch it, label all the boundaries, because you will need this to find the limits for x, y, z, or z, y, x here. Good? Okay. So let's suppose this is the region D, this is the shadow R. Now the next step is step 3, is to find the z limits, because I do the z first, right? That's the order we decided to do. Okay. To find the z limits, here's what you do. Pick a point, anywhere inside the shadow R. Pick a point anywhere inside the shadow R, then sketch a reading line. Not a reading line, sketch a arrow line upward in the positive z-axis direction. Sketch a arrow line in the positive z-axis. So draw an arrow line. Let's call this as M, and here draw this arrow line M, okay, through a point in shadow R. Okay, in the positive z-axis direction. Okay, so that's what you draw. Basically from here go up. Okay. This is basically what we call the first step of the scanning through this region D. If you look at this step right here, what we did is we basically go through the region D, and you have a first contact over here and then second contact at the top over there, or entry point and exit point. Okay. So now my first contact will give me the Z mean, and the second contact will give us the Z max. In this case, your first contact falls onto the bottom surface, F1 of XY, so that will be your Z mean. The second contact falls onto the top surface, F2 XY, so that will be your Z max. And this is why you label the boundaries or boundary surfaces or boundary lines. If you label them correctly, and you'll find the limits correctly, easily. So that's your first contact. As a matter of fact, the first scan, basically, when you go through this, what we just created, or what we scan through, is this green bar here, right? You have a green bar from the bottom to the top. So you scan through every point along this green bar. That's the first step scan. Or integration. You're integrating over the region R. Okay. So now once you find the Z limits, the next step is to find the Y limits. Okay. So how do we find the Y limits? To find the Y limits here is very much the next two steps, very much the same as the double integral now. You draw an arrow line. Use different color here. You draw an arrow line in the direction of the y-axis direction. Right, like a double integral. When you find the y-axis limit, what do? You draw an arrow line in the positive y-axis direction. So that line, here we draw it across the shadow R. So draw an arrow line across shadow R in the positive y-axis direction. That's the purple one. We draw it here. Good? Yeah. So once you draw this, and you look for first contact and second contact. Okay, first contact and second contact. So my drawing is not very precise. So let's say my first contact is this boundary G1x. Second contact is the G2x at here. So you get your Y mean. So first contact give you Y mean equal to G1 of x. Yes. Yeah, just let me write down this Y max and G2 of x. Okay, yeah. Here? Yeah. very procedural. Okay, very procedural. There's, if you follow the steps, I'm sure you will be fine. So G1 of x to G2 of x, okay, as the first contact and the second contact. Okay? Yeah. That's your y limits. And the last step is to find x limit. X limit is you're going to move that arrow line that you just draw across in this region, across the shadow R. So move or sweep the arrow line, okay, across shadow R. Then you find what's the two edges sandwiching this shadow R. They're always, basically this time is two constants. There's always constants for the last variable. The mean variable maybe is A, the maximum variable maybe is B. So it's like this. So basically over here you probably have two edges, one over here and one over here. So that's A, that's B. Okay. When you're sweeping that purple lines from left to right to find the edges here. Alright? Yeah. So I want you to visualize, instead of what I just described, finding the limit set here, I want you to visualize in your head how this solid region D is being created like using a 3D printer. Okay? So here's what I would print this region D here. I will print this green bar first, just a line segment. It's okay, right? That's the first step, finding Z limits. Then the second step, what I'm going to do is I'm going to go along the y-axis direction. So now you start to print many basically the green bars here. Right? That's the sweeping, right? That's the sweeping from along the y-axis set here. So after this step, guess what you have now? You end up with what? Just a flat green plate, right? Okay. And this last step, what do? You will move this. Basically, you will layer this now. You will layer this green plates, you know, the green ones, the green layer here, okay, from A to B, to recreate this solid object D. And that's what we call to scan through this region D at here. Okay, scanning through it, but without any redundancy. Okay. Yeah. So if you look at how the 3D printer works, it never go back to print, right? There's always layers upon it. Okay. Yeah. Okay, now let's take a look at examples now to apply the procedures. I'll give you a region D has a boundaries as following here. So y equal to x plus z, y equal to 1, and then z equal to 0. So here's the region D, bounded by these three things, 1, 2, 3, there's another one, x equal to 0. Okay, 1, 2, 3. Okay, 1, 2, 3, 4. So 4 sides give you a region D. So if you have this, the first step is you need to be able to sketch them. This is what I mean by, the preliminary things we have learned. You're basically using what we learned in the previous lecture here. Okay, so here's the Cartesian coordinates. So let's look at all the sides of this region D here. What are the sides? So first, y equal to x plus z. That's not a line. What does this equation represent? Plane. Okay, very good. So if you can always move everything to one side, you get x minus y plus z equal to 0. And how about this y equal to 1 and here? Where's 1? 1 is over here. Okay. If I draw it out here, and that's your y equal to 1, right? It's a line, but in 3D, it's what? It's a plane again, right? And z equal to 0, that's xy plane. So z equal to 0, that's xy plane. X equal to 0, that's what plane? The YZ plane. Okay? So these three are very straightforward here. Okay? And then it's a matter of this plane here. So how do you draw this plane? There are some tricks how you can draw the plane out here. Okay? But let me draw it first, and then we'll see why. Okay? Oops, what happened here? Just doesn't like drawing here. Okay. What the heck? All right. So basically, this plane will intersect 1, 2, 3, the other 3 planes at here. Okay. You can actually easily find the intersection. This point is what? Well. Take a short break. Is that a sign saying we should stop early? I'll keep trying. It's not fun. It's plugging the little bit power. When the video is running in the background, sometimes the computer is getting hot. That's probably why. Seriously? Where did my file go?